This section will provide some programming tips to help you program ONNC's NVDLA backend. Here's the outline for this section. First, we introduce NVDLA's register interface. Next, memory layout for three types of data cubes will be covered: the feature data, the weights, and the element-wise operands. Finally, I will describe three important data structures: the operation descriptor, the surface descriptor, and the data cube structure. To maximize execution efficiency and minimize programming delays, NVDLA uses two sets of identical register files for each hardware block. NVDLA calls them Group 0 and Group 1. They operate in a manner similar to the ping-pong buffer, which interchange roles after each operation completes. When the hardware block is in execution, the data path reads register settings from one group. Suppose this group is Group 0. At this moment, Group 0 plays the role of a consumer. The other group, Group 1, plays the role of a producer if it is available for CPU to program. The CPU always writes operator settings to the producer group, while the hardware data path always reads settings from the consumer group. When CPU finishes programming Group 1, it will set the OP-enable signal of Group 1 to high. After the hardware block finishes running the layer in Group 0, the consumer pointer will automatically switch to Group 1. If the OP-enable signal of Group 1 is high, the hardware data path will immediately begin running the next layer in Group 1. The example at the right-hand side depicts a sequence of 4 operators, OP1 to OP4. They need to be executed consecutively on the same hardware. The bottom 4 waveform shows how the programming latencies get hidden and do not contribute to overall execution time. All feature data in NVDLA must follow a specific order when stored in memory. Otherwise, the results may be incorrect. The order should be the same as how Convolution Engine outputs its results. Assume that there is a feature data cube of W by H by C. Here, W, H, and C represent the width, height, and channel size of the cube, respectively, in units of elements. We slice the cube in the channel direction at every multiple of atomic K elements. Recall that atomic K is the configuration parameter that represents the number of Mach units in the convolution engine. Now the cube is divided into several surfaces, each of the size of W by H by atomic K, except for the last surface, whose channel size would be a remainder equal or smaller than atomic K. In NVDLA, a cube size of 1 by 1 by atomic K is called an atomic cube. It is the basic data unit for all data processing. Cube data are also arranged in external memory in units of atomic cube. The specific order is shown in the figure in the right. Note that all atomic cubes must align at the atomic K address boundaries. Therefore, if the channel size is smaller than atomic K, as in the last surface, there will be bubbles in each memory entry, as shown by atomic cubes 193, 194, and 195 in the figure. Before concluding this slide, I would also like to quickly introduce two terminologies: line stride and surf stride. Line stride is the address offset between two lines in the same surface, while surf stride refers to the address offset between the starting point of two neighboring surfaces. Both offsets are in units of byte address, and neither have to exactly equal to the memory size of a line or a surface. Both line stride and surf stride are mandatory parameters that must be defined for every NVDLA data cube. The hardware engine relies on these parameters to find the correct location to access data in both DRAM and SRAM. NVDLA assumes by default that all data cubes are stored in the order described here. Because the sequence is the same as the output data, data reordering is unnecessary between different layers of operation. For example, a convolution layer can directly operate on an output data from a previous convolution layer without any reordering. Weight placement is more complicated because of weight reuse in the convolution engine. However, since weights are predetermined in the CNN model, ordering can be done at compile time without adding extra computation at runtime. Assume that the kernel sizes are kW by kh by c, where kW, kh, and c are the width, height, and channel size of each kernel, respectively, all in units of elements. In a convolution operation, the channel size of the kernel must match the channel size of the feature data cube. Assume that there are n kernels. We number them from k0 to kn-1. The parameters nc, kw, and kh are predetermined by the deep learning model. The n kernels are divided into groups, with atomic k kernels within each group. Within each kernel, the channel dimension is also broken down into multiple surfaces, just like the feature data cube. The figure on the right shows how atomic cubes are ordered in memory. The notation k0_1 refers to the first atomic cube in kernel k0. Within the same weight group, atomic cubes from the same position of different weight cubes are interleaved with each other. An important difference between feature data and weight memory layout is that there are no bubbles in weight memory. If the channel size of the weight cube is not a multiple of atomic k, weight elements are stuffed adjacent to its neighbor, regardless of whether the space fits the specific atomic cube. This is why you may see an atomic cube placed in more than one single memory entry, or a memory entry containing weight elements from multiple atomic cubes. Element-wise operands are used in SDP, which can perform element-wise add and/or multiplication between the feature data and an operand. Operands can be supplied in one of three modes: per layer, per channel, or per element. In per layer mode, every element of the input data operate on the same value, which is stored in a register repeatedly used on every element. In per channel and per element mode, the operands are stored in memory. In per channel mode, the same operands is shared between the elements in the same channel and repeatedly read from memory during execution. In per element mode, each element operates on a different operand, and every corresponding operand is fetched from memory exactly once. In a typical SDP computation subunit, the adder and multiplier share a common DMA interface to fetch operands from memory. Depending on which of the adder or multiplier are enabled, DMA will fetch respective addend or multiplicand as needed. If both the adder and the multiplier are enabled, the addend and multiplicand are interleaved in memory, as shown in the table on the right-hand side. To be more specific, this table describes operand memory layout when the operand's data is 16 bits floating point. One important goal of the ONNC backend is to set up each hardware engine correctly for a specific task. In order to do that, you need to know several things: the function or the expected behavior of the hardware engine, the accessible registers or parameters available, and the possible range or options of each register or parameter. Unfortunately, these information are not summarized in the NVDLA repo. They scatter over many different sources in the project. When developing the NVDLA backend, SkyMiser has put in a lot of effort to tackle this issue. Let me share a few things we have learned. In NVDLA's software stack, after the input model is compiled into the loadable file, the user and kernel mode drivers will read the settings in the loadable and activate NVDLA accordingly. Inside the officially released kernel mode driver, or KMD, there is an include file, DLA interface.h, which defines various hardware-related structures and parameters. One of them is called operation descriptors, or OP descriptor for short, such as the PDP OP descriptor, DLA PDP OP DESC. The members of OP descriptors gives us hint on the hardware parameters. For example, the first 7 parameters of the PDP OP descriptor are involved when the input image is too large for PDP's line buffer. In this case, the image must be split horizontally. Maximum width without splitting depends on other PDP parameters. Equations are documented in NVDLA's hardware manual on the official site. In short, the first 6 members in the PDP OP descriptor refer to the respective input and output width of each segment, as shown on the bottom left. Split num is the total number of segments the data plane is split into. If it is 2, only the first and last segment widths are valid. When split num is larger than 3, the middle widths are used for all segments except for the first and last. This slide shows an example of how to set up the operation descriptors when writing code for the NVDLA backend. PDP can be replaced by other engines in NVDLA to find information on other hardware blocks. Unfortunately, due to time limitations, we cannot go into further details. However, we encourage you to explore further on your own. In the DLA interface.h include file from the previous slide, there is another important structure called surface descriptor. It describes the data cubes used in each engine. Take the SDP surface descriptor, for example. The name of the structure is DLA SDP surface DESC. Each member structure in the surface descriptor represents a chunk of data that the hardware engine must access in memory. For example, surface descriptor of the SDP engine contains 5 data cubes, which are the source data cube for input, the destination data cube for output, and 3 operand data cubes for operands in the subunits x1, x2, and y. Each data cube has a dedicated DMA interface that handles data transfer, as shown in the figure. The structure DLA data cube defines information regarding NVDLA data cube. The structure defines the width, height, and channel dimensions of the cube, as well as its size in bytes and location in memory. Line stride and surf stride were introduced earlier. They enable the hardware to find the memory address of any element in the data cube. Memory type can be set to DRAM, SRAM, or another upstream or downstream engine in case of fusion. I conclude this section with the references. Thank you for your attention.